All right. So, welcome back. Here we are in our course. We have been talking about game playing and adversarial search. And so far, we have casted the sequential two-player game, adversarial game, as a minimax search task. And moreover, we have said that look, we can't search the minimax algorithm till the very end, and moreover, minimax is slow. So, in order to speed it up, we talked about alpha beta pruning, which effectively doubles the depth of the search that we can visit in the best case. But that is not sufficient either, because we cannot go till the end of the game, and that is because the games are long. The total number of steps that the game may take is very large, and so eventually we need to stop the search somewhere in the middle. And when we stop the search somewhere in the middle, we need to figure out what is the value of the current cutoff point that we are able to backtrack or back up, update up. And that particular value, evaluation function, is the key of game playing in some ways. If we have a really good evaluation function, we need not do any search whatsoever. We know exactly which move is the best based on just looking at, okay, if I take this action, my evaluation function says you will get this value. If I take that action, my evaluation function says you will get that value. So, let me not even do much search, let me just do one step, look ahead and figure out, this is the best action I should take. But of course, typically my evaluation functions do not get that good, and so I do some search, but then I have to cut off. And when I cut it off, I need to decide the value of that point, and that is computed by machine learning. And machine learning generally is this idea that a machine can learn based on experience or data. And in this case, the data can be historical games that have been played for this particular game between two players, or it could be your own experience that you are playing against yourself, you win or you lose, and you back up the values, and then you give your agent to your opponent, and then you start improving again. And that is sort of what the standard machine learning algorithm in this case would do. Right? Now, this and many other ideas came together in making a good chess player. Now, chess, as we all know, was one of the most important games to demonstrate that machine has intelligence. In fact, the history is not just 50-70 years old. The history dates back really old. Does anybody know about Mechanical Turk? Not of the Amazon variety. Does anybody know about Mechanical Turk? Yes. What's your name? Pratyush, tell me about it.
So it was a fake chess player. It was a fake chess player. It was a big box inside which a man sat and played chess.
That's right. So Pratyush says it was a fake chess player. There was a man sitting inside a big box who was playing chess. So the story is that this goes back to late 1700s actually. I think this happened in Europe, where they created this very elaborate mechanism so that nobody could find that there could be a human sitting inside. And this human had very short height, because of which he could squeeze inside this box. And there was an elaborate gadgetry that somebody opens the door, it looks like just some gears and so on and so forth moving around, and there were powerful magnets such that this player could play the game sitting inside. And so, and this player was a Turkish person, which is why once this secret was revealed, this particular gadget started to be called Mechanical Turk. And the idea is that you think that the machine is playing. So, what would happen, this magician or this person will take this big box to say that, oh, I have made a machine which can play chess. And people will be like, oh, of course, that is not possible. So, they will play a game of chess with the machine, and the machine will win, because the Turk actually knew how to play a good game of chess. And so, everybody would get amazed. They would open the door here, they would open the door there, they will be able to see through. However, this was arranged right, using all the tricks of magic at the time, and they would feel like the machine is playing this. It is a mechanical device that is playing the game. So, eventually Mechanical Turk started to be called as a general word for the phenomenon when you want machine to do something, but eventually at the back end a human is doing it. Does anybody know about Amazon Mechanical Turk? Nobody? Okay, this is your homework. You must read about Amazon Mechanical Turk just for the general knowledge. I mean, these things are things that are happening around us. So, I mean, I am not saying that Mechanical Turk just started today. Mechanical Turk started, in early 2000s, in the 2006, 2007, I think time frame. But the idea is that this is a marketplace for people to work, right. So, you have a task, let us say you want to label training data, or you have images, or you have bills that people have. You are Magic Pin, I do not know if you know. Do you know about Magic Pin? Dine Out? You know about Dine Out, okay, good. Like which world are you living in? So, Magic Pin, Dine Out, all these are mechanisms where you eat out. You take the bill and you take a picture and you give it to Magic Pin and say, this is how much I paid 1000 rupees for this meal, and Magic Pin will give you some points back. And you can keep accumulating your point. What is in it for Magic Pin? Magic Pin knows who is eating where, what kind of food you like, what kind of food is sold in this restaurant, and what is the typical purchasing power of you, what is the typical price of meal of the restaurant, etc., and then they can monetize this data. Okay. Long story short, suppose you did not know how to do OCR, or your bill was the picture was not taken just perfectly and so on and so forth. What would you do? You will try to give it to the machine will not be able to give you the correct amount. They will not be able to verify. I mean, they need to verify. You say that I spent 1000 rupees, but eventually you only spent 20 rupees, then you should not get credit for 1000 rupees, right. So, essentially what we do is we give the task to the machine, but behind the machine sits a human sometimes, and this human actually does the labeling. And now this is not secret, everybody knows that there is a human behind, right. And one such marketplace is the Amazon Mechanical Turk, and this whole phenomenon comes into this for of crowdsourcing, that you do not know who is doing the task, somebody from the crowd is doing the task, but somebody is doing it. It is like you ask a question on Piazza and the TAs do not get the time to respond, I do not get the time to respond, but one of your fellow students responds and gives you the answer. But this fellow student chooses to not put in their name on the response, it is anonymous to you, then this would be crowdsourcing. You had a question, the crowd gave you the answer. In fact, the crowd can come in and say, no, this answer is correct, they will cut it, they will improve it, they will edit it, it will give you a better answer. So, Piazza is one way of crowdsourcing information. Another famous way of crowdsourcing information, Wikipedia. Before Wikipedia, there was Encyclopedia Britannica. I think they are going out of business, or if they are not, they are the only encyclopedia not going out of business, something like that. All encyclopedias have gone out of business. At the time, there were people who would write encyclopedia by hand. I mean, of course, Wikipedia is also written by hand, but individual people who will be responsible for individual essays and so on and so forth, they will have some quality control, they will be paid huge amount of money to be writing in Encyclopedia Britannica. Now, anybody can go and edit anything. But the point is, then somebody else will moderate it, and then there will be a mechanism which will vet it, and so this is all a crowdsourced mechanism. The quality control is crowdsourced, the original sourcing of the article is crowdsourced. As an event occurs, quickly it gets onto Wikipedia because it is crowdsourced. If there was a person responsible for that article who was always editing it, you would be dependent on that particular person to actually make the edits, that would not be scalable. So, when crowd comes together, a very interesting and nice properties happen. In, for example, in Mechanical Turk, you could be sitting in Africa, you could be sitting in Eastern Europe, you could be sitting in the Philippines. You may not have sources of income, but you may have an internet. And if you have internet, you can go to Mechanical Turk, you actually get an account and you can start getting paid for the small amounts of work that you do. And in many economies which are not very rich, even though the amount of money you make per task is small, that adds up and that actually increases the quality of your life. So, it was seen about a few years ago when this demographic study was done, that a lot of people on Mechanical Turk were from India and Philippines and different countries where the overall cost of living is low. So, it democratized work actually to some extent. Anybody can get work, and that's the beauty of it if you have some skills. So that idea came from this idea of mechanical Turk, which was a chess player where you were giving it to machine, but internally there was a human doing it. And so this whole intention that look, we need to make a good chess player was very important in the minds of AI researchers, because the history of mechanical Turk and history of chess as an important game for intelligence had been around. And I also told you that even from the very beginning, when the word AI was coined and AI as a field started, people were trying to play chess. And of course, minimax came very quickly, right? It's a theoretical understanding of how to even go about modeling a game, that came in pretty quickly. And in fact, Samuel's checkers program talked about evaluation function learning very quickly, because you could not go till the very end, you always had to figure out what to do in the middle, and the idea of machine learning came very quickly, right. But then the other ideas took some time to come in. For example, alpha beta search came only in 1966. So it took about 10-15 years for somebody to recognize that you can actually keep bounds and so reduce the amount of search that we need to do. Then the idea of transposition table became very important. See, in chess and in a lot of games, for example, I make move 1, you make move 2, I make move 3 and you make move 4. That is possible, and equally possible or often possible is that I make move 3, you make move 1, move 2, I make move 1, you make move 4. You will get to the same point, like I move this pawn, you move this pawn, I move this pawn, you move this pawn, or we do it in the reverse order. I move that pawn first, you move that pawn first, I move this pawn second, you move this pawn second, you will get to the same state. So in games, and I can actually go back and forth, I moved my knight and I moved it back, I moved my knight and you moved it back, and so on and so forth. So these kinds of cycles are actually extremely common in a game. And we know that when we do search, when we do tree search, then for each path for reaching a node, we are creating a new node. For each path to reach a board position, we are creating a new node, and that's not very good. It's not very scalable. So the idea that we can store some memory and do some duplicate detection came in 67, and in the context of games, it was called transposition tables. So basically, if two board positions are the same, let's not create a new node for it, let's just maintain the evaluation function and the best action to do there separately, right. Then the idea of iterative deepening came, and it took another 8 years to come in. So then iterative deepening happens, so you will go one step, then you will go 2-step search, and you will do 3-step search, and you will reorder your children based on the search that you did in the previous iteration. Then many other ideas started to come in the 80s. Some ideas were, the idea of end game databases, opening databases. Some ideas that, one move may be so good that you can always look at it, singular extensions. Then when bigger supercomputers started to happen, then the idea of search can happen in parallel. We don't have to do it on one CPU, we can do it on a supercomputer, etc., etc., etc. So when all such ideas started to come together, the chess players started to become better and better and better. In fact, the deep blue player is really, if you think about it, it is some combination of, okay. So initially it would do an opening database. So for the first 20-ish positions, it sort of knows what to do. There's a few strategies that it will follow. It will follow those strategies. So it knows what move to do, and based on what you do, it doesn't have to do search, it sort of knows what to do. These are best practices in the field of chess. You sort of know how the openings work. Towards the very end, actually, you can pre-compute all databases, all possible games. So let's say all possible games of 5 and 6 pieces. That's not a large number. Let's say I just think about, okay, I have a knight and king, you have a bishop and king and a pawn, okay. Let's say, we randomly place them, who wins? That's one ending game database. I randomly place them differently. Let's say I have another ending game, and I say I have 2 pawns and a king, you have a king and a queen, okay, let's see who wins. So when the game is at the very end, you can completely search. You don't need evaluation function at that time, you can completely search the game, because now your number of steps is not very much, and so then you can completely search it and you can figure out who is going to win. So now it's like this, that in the beginning I know what to do, sort of. In the end I know what to do, sort of. I have pre-computed it, I have memorized it. I have stored it in my databases, in the opening database and in the end database. What do I do in the middle is actually really complicated. Because what do I do in the middle? There are so many different kinds of middle positions, and the game is really far away to finish. So, it is like I am talking about a lot of look ahead and lot of starting points. I cannot store that in a database. There people used all the tricks that you had: minimax, alpha beta pruning, evaluation function, transposition table, iterative deepening, singular extension, this, that and the other, everything. So, really in practice chess got divided into 3 steps: the opening stage, the middle stage and the end stage. The opening stage was clear what to do, the end stage was pre-computed and clear what to do. The magic happened in the middle stage. And as you think a little bit, you realize that this phenomenon is actually really valuable for people also. Say you are in a race, just think about it, just say, let us say we are talking about a 2 km race or a marathon or a half marathon, something like that. When the buzzer goes and you start, you have a lot of excitement, you have a lot of energy. Why? It is just starting out, there is passion, I want to finish this, I want to win this, whatever it is. Now, when you see the finish line some distance away, then you put all your effort into it. You say, okay, that is the end, I have to go full throttle, I have to somehow get there as fast as I can, you get motivation to get there. In the middle is what differentiates the successful from the not, in my opinion. Because in the middle it is very hard to maintain motivation. There is no end in sight, you have been running for a long time, you do not know how much you have run, you do not know whether you are going to make it or not, there are lots of questions, there is so much confusion, there is so much insecurity. That is when you need the maximum amount of intelligence. You need to somehow say, okay, I will keep going. At least in marathon, you know which direction you have to go. Suppose you did not know where the goal is. Let us say you did not know where Taj Mahal is, you are just doing random walk and you want to eventually find Taj Mahal. I mean, it is possible, right? This is how many of these games are. You have to finally win, you do not know where the win is. And so, when you started out from home, you said, okay, I will go in that direction, I will definitely find Taj Mahal. If you start looking at Taj Mahal and the Taj Mahal is, you can start to see it, you sort of know, okay, I am going in the right direction. Now, if I go here, I will probably reach Taj Mahal. Now, you have newfound motivation. In the middle, when you have come from your home a long way, there is no Taj Mahal, you do not know whether you should be going in this direction or that direction, that is where the most intelligence is needed. So, in life, think about it, when you think that the going is getting tough, when you think that you do not have an end in sight, when you think that when you ask questions of whether you are doing the right thing or not, you are in the middle game stage. And taking right actions in the middle game is what separates a better and more intelligent person or thing from the less. Because in the opening game everybody is using the opening game database, in the end game everybody is using the end game database. It is only in the middle is you have to do search, you have to think, you have to evaluation function, you have to have learned from experience. That is where you figure out whether you are a good player or not a very good player. Okay? So, always keep this in mind. Let us see some problems that happen when we do this middle game search, right, when we do this minimax search. One of the problems with depth first, fixed depth search. So, we are always saying, okay, I will go to 8 ply or I will go to 6 ply or I will go to 10 ply and I will stop. Now, there is a problem there. The problem is that when we are only looking at n moves ahead, it is possible that we are not able to observe catastrophe that is going to happen just 1 move later or just 2 moves later. It is possible that we think, for example, in this example, black can give many consecutive checks before white escapes. So, black thinks, yes, I can kill the king of the white, but it cannot. If it searches further, it will realize that the white will be able to escape. So, therefore, this whole plan of trying to give checks to the king is not very good, but it will not know because it is only searching till a certain depth. So, it happens in both directions. A move may look good because I have looked at only a limited amount of time, and then it may turn out to be bad, or a move may look bad, but if I had looked a little longer, I would have found that yes, I actually was able to do check and mate or whatever. This is called the horizon effect. For example, in this case, if I do one action, I lose the queen. If I do another action, I lose the pawn until blue line, until the cutoff. But if I play further, I lose the queen. So, which action should I do, left or right? Left action. I should do the left action. I should just let the queen go, and save the pawn, but I only search till the blue line depth. So, I do the right action, and when I do the right action, I end up also losing the queen later, right. In fact, you will also recognize that another level of intelligence between people is how far they are able to look and think. We have in Hindi a concept called Doordarshi, somebody who is able to look really far into the future. Now, I am not talking about astrologers. Somebody is able to anticipate that, okay, if I make this action, this person will get unhappy, they may do these kinds of things that will make that person unhappy, that person may do some things which will really hurt me, for example. And this long chain of what the consequences are going to be, we normally are not able to think about, but some people are able to think about. That is what movies are made of, right. And so, how far you are able to look into the future determines how intelligent you are. So, this is called horizon effect, that how far you are able to look into the future and therefore, what action you do. And so, what can you do? I mean, of course, horizon effect will always happen because we are always going to search till a very specific depth, but how can we mitigate this? What can we do to reduce the effect of horizon effect? Any suggestions? So, this is at this point algorithm design, heuristic design. What would you do if there was if you wanted to reduce the trouble that you will get or reduce the effect of horizon effect? Sorry? Singular extension. What is singular extension?
Like some move that is looking good, we try to search with higher depth in that.
So, that is not called singular extension, but that is called secondary search. What is your name? Cheyenne. So, Cheyenne says, use the wrong term, but Cheyenne says search further down the selected path. That is called secondary search. It is sort of saying, look, I think this is the good path up to this depth, but maybe it is not. Let me verify it. How do I verify it? I just play the game a little longer from that point onwards. Just develop that particular path, and if that particular path still looks good, then we are okay. If that particular path suddenly starts to look bad, then we are like, oh no, something was going to go wrong. I have figured out that it is going to go wrong. Let me backtrack and do something else, figure out a different plan of action. So, that is called secondary search. There is another search which is called quiescence search. Okay. Basically, what it says is that some board positions are too dynamic, like I have just given check. I do not know if the king is going to save itself or not. I do not know whether, right, it is a very complicated board position because I do not know what has happened, have I come to some level of stability or I have not. So, this level of stability in the context of game playing is called quiescence, right. So, I have a secondary procedure which figures out whether this board position will be called stable or not, and if the board position will not be called stable, I will not cut off there, I will keep going until I get to a stable position. So, I will do unequal searches. So, in one path of action I may just go to search depth 6, in another path, because in search depth 6 I get non-quiescent position, I keep going and maybe search till depth 10 to get a quiescent position and then back it up. Okay. So, as the slide says, this involves searching past the terminal state nodes and testing all the non-quiescent or violent moves. Violent moves means that the board is unstable until the situation becomes calm, and only then apply the evaluator. So, you do not have a fixed depth, you have a variable depth based on whether your cutoff is at quiescent position or not. So, this enables programs to detect long capture sequences and calculate whether or not they are worth initiating. This expands searches to avoid evaluating a position where tactical disruption is in progress, where lots of things are happening. I am killing you, your pawn, you are killing my knight, I am killing your bishop, blah blah blah. Right? And then there are many other refinements, right. So, in alpha beta pruning, we are only able to prune if it is guaranteed to be suboptimal, but this guarantee is too strong a word. So, we probabilistically cut it. So, it is not guaranteed, but alpha beta is sort of in a bound, in a region, there is a very small band where this might be a good optimal move. Let me just probabilistically cut it nevertheless, right. So, that is called probabilistic cut. Then you have opening databases, endgame databases, which I already talked about. There is something called singular extensions, where there are some obviously good moves and you just maintain those obviously good moves and then you apply them at cutoff. Right. So, many such ideas got developed in the field of chess, and a lot of this work was happening at IBM at the time, because IBM was really interested in making chess player that beats humans to showcase its strength and power position in AI. In fact, if you look at traditionally from the 50s up to the 90s and even until the 2000s and early 2011-12, when Watson happened, IBM has consistently come up with big demonstrations which have shown its power and its ability in artificial intelligence. In the very recent times, Google and Facebook and so on and so forth have now started to come up with really interesting AI technologies. For example, DeepMind did the Go player, but for big demonstrations typically IBM has done more than most. Let me talk a little bit about endgame database. So, somebody came up with all 5-piece endgame databases, did the full minimax search, at that point figured out who wins. Similarly, Louis Stiller did all the 6-piece endgame databases. And in fact, what Louis Stiller found, that if you search long enough, if you are white, you can force black to lose 90% of the time. 90% of the endgames that came up in gameplay, even though they may have been drawn in actual game, were wins for white. And that came up with the question, is perfect chess a win for white? We do not know the answer to this question. We have not been able to prove either way. But it is possible that if the universe started playing the game of chess and used all its atoms to play the game of perfect chess, we may end up with the answer that, oh, if you just play perfectly, white will always win. We do not know that. Here is what is called the monster endgame. In this monster endgame, there are 6 pieces, 3 of white, 3 of black, and it was considered to be a draw, I believe. But people showed that if you search long enough, in particular 255 plays, then white can force a win. So, now humans may not have been able to even get to this 255 long move play sequence. So, they may have done a draw, but when you use the machine, you figure out, no, this particular game position takes 255 moves, but white wins, and many such positions exist. So, summing up, there have been a lot of deterministic games. We have spent some of the today's lecture on chess. Some of the ideas are also valid in many other games. Okay. So, we will stop here. Thanks.